Hello everyone. I welcome you all for this TA session of NPTEL course FEM for the January to April 2025 batch. Got a bit late to start today's class, but no worries. Let's start the class. So this is week number 11 lecture. Let's start the class now. So I haven't prepared the questions in advance. I'll write the questions and we'll discuss them. And just now, so the question number one is for the beam shown in figure. Determine the nodal displacements and slopes, forces in each element. And the reactions. So the beam which is given is like this. This is your beam. One side is hinge, one side is roller, and a spring is also attached in the middle. So this is 6 meter, this is 6 meter, and spring K is given as 10 kilonewton per meter, and the loading which is given is like this. Triangular loading is there. Same way, second span also a loading is there, same triangular loading, and its value is mentioned as 10 kilonewton per meter. 10 kilonewton per meter. Now other things which are given are as E equals to 210 GPa, I is given as 4 into 10 power minus 4 meter square. And if you talk about the nodes, so this is 1, this is 2, this is 3, and this is 4. Okay, so just look at the question, then we'll start the solution of it. So what the question is saying is just the simple beam problem attached with a spring, and you have to solve the unknown slopes, forces, and the reactions using FEM. So this is the basic problem we used to solve in structural analysis. Now what we have to do, we have to solve it by FEM. So let's start solving the question. So consider element 1. So what we can do, we can take this element as 1, we can take this element as 2, and third will be the, surely will be the spring as well. So let's start. Consider element 1. From node 1 to 2. So This is the node 1, this is the element 1. So node 1 and node 2 are this, and we'll put the loading as well, which is 10 kilonewton per meter. Now what you have to do, you have to specialize the degree of freedoms, which is V1, phi 1, V2, phi 2. Now we know the stiffness matrix for this beam. We can directly write it. So okay, let's start writing. We all know this. This will be K1, and outside it will be EI by L cube. Now 12 6L minus 12 6L, this is 6L, 4L square minus 6L, then 2L square minus 12 minus 6L, 12 minus 6L, 6L, 2L square minus 6L, and 4L square. So the degree of freedoms which will be corresponding to it will be V1, phi 1, V2, phi 2. Similarly V1, phi 1, V2, phi 2. So this you all know about this. Let's solve the uh, values for it. So the first term we have to compute is 12 EI by L cube, which will be 12 into 210 into 4 into 10 power 8 divided by 6000 whole cube. So when you'll solve it, you will get it 4.67 kilonewton per mm. Another thing, 6 EI by L square, which will be 6 into 210 into 4 into 10 power 8 divided by 6000 power 2. So when you will solve it, you will get it as 14,000 kilonewton. Now one more we have to solve is 4 EI by L, which is 4 into 210 into 4 into 10 power 8 divided by 6000, and you will solve it, you will get it 56 into 10 power 6 kilonewton mm. Then 2 EI by L, that will be 2 into 210 into 4 into 10 power 8 divided by 6000. Solving, we will get 28 into 10 power 6 kilonewton mm. So I have maintained the units for each of the terminology. Now when you substitute these values in the stiffness matrix, what you will get, you will get this solution, which is 4.67 14,000 minus 4.67 14,000 14,000 56 into 10 power 6 minus 14,000 28 into 10 power 6 minus 4.67 minus 14,000, then it will be 4.67 and minus 14,000, then 14,000 28 into 10 power 6 minus 14,000 and 56 into 10 power 6. And close the braces and again write the degree of freedoms. Phi1 v1 phi1 and v2 phi2. Similarly v1 phi1 v2 phi2. So now we have the k matrix of the element 1. So it's to check whether your matrix is correct or not. I think you are well versed with it now. So what you have to check? You have to check whether the K matrix is symmetric or not. So you can directly see the K matrix is symmetric here. Okay, so this means your one check is good. So let's start with the second element. So similarly for element 2, now we'll take this element, put the loading, kilonewton per meter. This will be element number 2. So this is node 2, this is node 3. When you will put the degree of freedom, this will be v2, this will be phi 2, this will be v3, this will be phi 3. Now since we have got the stiffness matrix of first element, same will be for the second element. So we can write it k2 as 4.67 14,000 minus 4.67 14,000 56 into 10 power 6 minus 14,000 28 into 10 power 6 minus 4.67 minus 14,000 4.67 minus 14,000 then 14,000 28 into 10 power 6 minus 14,000 56 into 10 power 6. Just the change what will be happening from k1 to k2 will be the degree of freedoms. Here it will be v2 phi 2 v3 phi 3. Similarly v2 phi 2 v3 phi 3. Okay, now two elements are over. Now what you have to see? You have to check the stiffness of the spring element. Okay, for spring element, so for spring element the K matrix is very simple. We know it will be K minus K minus K and K. So degree of freedom which will be corresponding to it will be V2 V4 and V2 V4. I don't need to particularly show you the degree of freedoms. You all know about that. So when you will give the values of K, you will get it as 10 power minus 2 minus 10 power minus 2 minus 10 power minus 2 and 10 power minus 2. This will be V2 V4 V2 V4. Now next step, what it is, you have to combine all the stiffness matrices to get a global stiffness matrix. So the way I have discussed many times, so I think that you are well versed with it right now. So I'll directly write the K matrix, the global K matrix. So I'll refine one more time. The degree of freedoms which are corresponding to each K, you have to add them add their values. Otherwise you have to just put that value. Okay, so degree of freedoms will be V1 phi 1 V2 phi 2 V3 phi 3 and V4. So let's put the values. It's 4.67, then 14,000 minus 4.67, then 14,000. V3 will be 0, 0, and this will also be 0. Now again, this will be 14,000. This will be 56 into 10 power 6, and minus 14,000, and 28 into 10 power 6, and it will be 0, 0, 0. I write this as symmetric, and it starts giving you the diagonal terms between 9.35, then 112 into 10 power 6, then it will be 4.67, then 56 into 10 power minus 6, and 10 power minus 2. You close the bracket and fill the other terms as well. So this will be 0. This is minus 4.67, and minus 14,000, then 14,000, then minus 10 power minus 2, and 0. This is 28 into 10 power minus 6, then minus 14,000, and 0, 0. Rest all terms are symmetric, so you can fill the matrices. Now you got the global stiffness matrix. Let's see what question is asking. So it is asking you the nodal displacements and slopes and the forces. So this means you have to solve the full problem of FEM. Now the next problem you have to get, next step you have to get the load vectors. Now let's take a new page for that. Okay, so load vector. This is your beam. This is your loading. 10 kilonewton per meter. This is MB. This is RB. This is RA. And this is MA. Okay. So fixed end moment we know. For varying distributed load, MA will be minus WL square by 20. This all we know from the structure analysis subject. So let's start putting the values in it. So it will be minus 10 by 1000 into 6000 whole square divided by 20. So it will become minus 18,000 kilonewton mm. Similarly, MB will be WL square by 30. So it will be 10 divided by 1000, then 6000 whole square divided by 30. So it will give you 12,000 kilonewton mm. Okay. So next we have to find the reactions as well. So will summation of MB will be at 0. So this will be RA into L, which will be equals to WL square by 12 plus WL by 2 into 2L by 3 minus WL square by 30. So what this is, we are making moment at about B is equal to 0. One is VDL, one is RA, and one is MA. So we have written the contribution from each of the term. Now when you solve it, you will get RA as 7WL by 20. So after putting the values, 6000 divided by 20, it will become 21 kilonewton. Okay. Similarly, RB will be WL by 2 minus RA, which will be 3WL by 20, and you will put the values. So you will get it as 9 kilonewton. So you can see the total sum is 30, which is the total load which is applied on the beam. So now we have to see the action from these reactions, which will be, so this is the beam, this will be 18,000, the opposite reaction which is acting by the beam. So the action I have written. Now this is for element number 1. For element number 2 it will be, so it will be 18,000 in this direction, similarly 12,000 in this direction, this will be 21 and this will be 9. Also for element 3, reaction force at node 2 will be balanced. Therefore it equals to 0. And at node 4, reaction will be R4. I hope you are getting all the things. Now when you will put the load vector along with the reaction forces, what simply you will get? You will get R1 minus 21 minus 18,000 minus 18, 0, R3 minus 21, 18,000, R4. Okay. Now you have the load vector. Now what you have to do? You have to solve this. KD is equal to R. So if you see the K matrix, this is the this big. Now what all reaction we know? We know okay, we know V1 is 0, we know V3 is 0, we know V4 is 0. 3 of the V are 0. So we'll write here V1 equals to 0, V3 equals to 0 and V4 equals to 0. Let's reduce the global stiffness matrix along with the what I'll do, I don't write the full K, but I'll give you the degree of freedoms full. So phi 1, V2, phi 2, phi 3, V1, V2, V3, and the RHS will be minus 18,000, minus 18, 0, then 18,000, R1 minus 21, R3 minus 21 and R4. So what I have done, I have shifted the known values of displacement downwards. Accordingly, K should be shifted. I think you all know all this by now. So this is shifted K. So to solve this, you have to take the unknown displacement first. So when you will write K reduced for the unknown displacement, it will be 56 into 10 power 6 minus 14,000, then 28 into 10 power 6, 0, minus 14,000, 9.35, 0, 14,000, 28 into 10 power 6, 0, 112 into 10 power 6, 28 into 10 power 6 and 0, 14,000, 28 into 10 power 6, 56 into 10 power 3. So this is the K reduced, and here it will be phi 1, V2, phi 2, phi 3, and the RHS will be minus 18,000, minus 18, 0 and 18,000. Okay, so now you can solve the problem. You have four equations, you have four unknown. By solving either in MATLAB or some computational software, solving we get phi 1, V2, phi 2, phi 3, which will be equals to minus of 0.0032 radian, minus 11.52 mm, then this will be 0 and 0.0032 radian. So you got the unknown displacement and the beam. Now you have to find the reactions. For finding reaction, you have to use the rest of the equations. So I don't okay, I'll put the that also. So we have to use the other okay. So when you solve it, you have to write 14,000 minus 4.67, 14,000, 0, then 0 minus 4.67 minus 14,000, then minus 14,000, then 0 minus 10 power minus 2, 0, 0, and this is the okay. So here it will come, phi 1, V2, phi 2, phi 3, and RHS will be R1 minus 21, R3 minus 21, and R4. So simply when you solve it, you will get R1 as 29.94 kilonewton. This is just the system of linear equation you are solving. So R3 will be 29.94, this also, and R4 will come as 0.1152 kilonewton. Okay, so you have got the reactions as well. So all these values were asked in the question. So what we have done, we have solved a full beam problem using FEM. Now let's go to question number 2. Okay, so what you have to do in question number 2, we have to derive the equations for the beam element on an elastic foundation as shown in figure, using principle of minimum potential energy, where or here Kf is the subgrade spring constant per unit length, and the potential energy of beam is pi p from 0 to L, half of EI V double dash whole square dx plus 0 to L kf V square by 2 dx minus 0 to L wv dx. Okay, so the figure I'll make it in the next page. So this is the beam on the elastic foundation. Okay, so this is the now loading. What it is given is like this, which is wx, and the length is L of the beam. This is moving at x, and this is kf. So I'll give you 2 minutes to read the question, then we'll start the question. Just read the question once, then we can start. Okay, now let's start solving the problem. So potential energy, it is given like this: 0 to L half EI V double dash whole square dx plus 0 to L kf V square by 2 dx minus 0 to L wv dx. Now we know V is equal to ND, which is V is equal to N1 D1, N2 D2, and so on. Also, when we double derivate it, d2v by dx square, we get it as bd. For beam, we have to do the double derivative. So we'll put these values in the potential function, so that it will become half of 0 to L d transpose B transpose EI B d dx plus kf by 2 0 to L d transpose and transpose and dx minus 0 to L d transpose and transpose w dx. So for beam, we know n equals to n1, n2, n3, n4. So where n1 is 1 upon L cube, 2x cube minus 3x square L plus L cube, n2 will be 1 upon L cube, Lx cube minus 2L square x square plus L cube x, n3 is 1 upon L cube minus 2x cube plus 3L x square, then n4 is 1 upon L cube and Lx cube minus L square x square. Okay, so we have written the shape functions of the beam element. Now we have to minimize the potential energy. Okay, so when you do it, you will get it EI 0 to L B transpose B dx plus KF 0 to L N transpose N dx. Inside outside D will be there. It will be equals to 0 to L W and transpose dx. Okay, so it can be expressed as K D equals to R. You can see na, this is K and this is D and this is R. Okay, so one by one, let's take the terms. The first is EI 0 to L B transpose B dx. So the representation of K matrix is the representation of K matrix. So it will be EI by L cube 12 6L minus 12 6L and 6L 4L square minus 6L 2L square minus 12 here minus 6L 12 minus 6L and 6L 2L square minus 6L 4L square. Okay, another thing is KF N transpose N dx. So for we'll solve the N transpose N. So what we'll get? We'll get 1 upon L power 6 2x cube minus 3x square L plus L cube whole square dx. So when you'll solve it, you'll get 1 upon L power 6 4x power 6 plus 9x power 4 L square plus L power 6 minus 12x power 5 L minus 6x square L power 4 plus 4x cube L cube dx. So the solving of it will become 1 upon L power 6 4x power 7 plus 9x power 5 L square by 5 plus L power 6x minus 2x power 6L minus 2x cube L power 4 plus x4L cube from 0 to L. We are putting the doing the integration and putting the limits now. Then 1 upon L power 6 4L power 7 divided by 7 plus 9L power 7 by 5 plus L power 7 minus 2L power 7 minus 2L power 7 plus L power 7. So it will become 13L square by 35 L power 6, which will become 13 by 35 L. So this is the answer for N transpose N. So what matrix will be formed? I'll write the solution of that now. It will be KF 13 by 35 L 11 by 20 L square 9L by 70 minus 13L by 420 11L square by 20 L cube by 105 13L square by 420 minus L cube by 140 9L by 70 13L square by 420 13L by 35 minus 11L square by 210, then minus 13L by 420, minus L cube by 140, minus 11L square by 210, and L cube by 105. So beside this we have R vector also, which is 0 to L W and transpose dx. So this will be simply WL by 2, WL square by 12, WL by 2, and WL square by 12. So this is the finite element formulation. Also the D vector will be V1, phi1, V2, phi2. So we have done the finite element formulation for the elastic foundation, elastic beam on the beam on the elastic foundation. Okay, so let's see the next question what it is. So what next question says, derive the equations for the beam element on elastic foundation using Galerkin's method. Basic differential equation is EI V double dash or double dash minus W plus KFV. So we have solved beam on elastic foundation using FEM. Now it is being asked to solve the problem by Galerkin's method. I hope you remember the Galerkin's method, which is taught in the class as well. So let's start solving the problem. So this is the differential equation which is given. Let's assume weight function as z. Why I'm taking z? So that to avoid the confusion, because v and w both are there, so it will be very difficult to differentiate if you take weight functions as w or v. So let's start with a new variable which is z, so it will be easily differentiating from the other variables. Okay, so this will be 0 to L z EI V double dash 2 double dash plus W minus KF V dx is equal to 0. Now 0 to L Z EI V double dash dx plus 0 to L ZW dx minus of 0 to L KF VZ dx equals to 0. So we have separated each term. Now we can solve it separately. So what we can do, we can assume EI as a function of x. So it won't come out of your integral. So when you solve the equation, it will be z EI v double dash dash from 0 to L minus z dash EI v double dash 0 to L plus 0 to L z double dash EI v double dash dx plus 0 to L zw dx minus 0 to L kf zv dx equals to 0. So in matrix form what it will be, in matrix form let's write it. Then we have to write it as Z transpose EI V double dash single dash from 0 to L minus Z dash transpose EI V double dash 0 to L plus 0 to L Z double dash transpose EI V double dash dx plus 0 to L Z transpose W dx minus 0 to L kf Z transpose V dx equals to 0. Now assuming V equals to N D V double dash is equal to N double dash D and V double dash equals to, this will be B of D. So by Glarkin method we know Z will be equals to N, and then we can substitute each of the term in the equation, so that will become N transpose EI B dash D 0 to L minus N dash transpose EI B 0 to L plus 0 to L B transpose EI B dx, or this will be, then the other terms, which is N transpose W dx minus kf of 0 to L N transpose N dx with D equals to 0. Now you can use the terms in terms of in form of B, so that will be 0 to L B transpose EI B minus kf N transpose N with dxd equals to 0 to L minus N transpose W dx plus N dash transpose EI B of D 0 to L minus N transpose EI B dash. Okay, so simple. Again you can see the equation can be represented as K D equals to F. So all problems can be represented by KD is equal to F equation, and this we have done in this question as well. Okay, so what I did today in class, I have solved full FEM problem, one with the beam with the spring. Other two problems were with the beam with the elastic foundation, one using the FEM solution, one using the Glarkin method. So now you can use this method to formulate any problem or solve any problem using Glarkin, FEM, and get the whole solution from starting. So since it's the ending of your course, so now you should have a hands-on on how to start with the discretization of a problem. Means whatever problem is given, you should have a hands-on on discretizing into the elements, put notes, and each element you have to solve it separately. Then what you have to do, you have to make the K matrix of the single elements, then make it combine all the matrices, all the elemental stiffness matrices to get the global stiffness matrix. Similarly, on the RHS side, what you have to do, You have to get the local load vector for each of the elements, then combine it to get the global load vector, and by combining all this you will get the kd is equal to f equation. To solve that, you know the Gauss elimination method that can be used to get the solution. So that's all I have for today's class. If you have any problem, do visit the video, pause it, and you can have a look on it. You can even send the mail in the forum, or you can just ask me in the next class also. I'll wait for 5 more minutes. If anyone have a doubt, do have a look, and you are free to ask now also. I'll scroll the pages. If you feel any doubt, you can stop me by then and ask the problem. Okay, since there are no doubts, I'll close this session for now. Since the exam is approaching, do post your doubts and queries, or one more class is left. If you have doubts and don't want to post, you can even join the next class and get your doubts cleared. Thank you for now. I'll close the session.